So in this problem, we have 50 kilogram cabinet. Mu equals 0.8. And so I give you the sum of forces in the x direction will be max. And so what's that going to be? Well, if you remember from our previous work, some fraction of the weight force is directed along the ramp, okay, and ends up being a sine instead of a cosine because we tilted our axis, and fighting that would be the force of friction. And when they're in balance, it's possible to have motion, so they could have a constant speed. So this is a situation where it's in equilibrium, where the friction and the weight force match, so it wouldn't be moving. And then just like it has on your handout, you have the y forces, and in this case you have the upward normal force, and then if you remember, the part of the weight that's perpendicular to the ramp is a cosine instead of sine like we're used to it being, and also it's not moving in that direction through the plane of the ramp, so acceleration in the y direction is also 0. All right, and so we go through some rigmarole, and so I'm going to skip to what you can see on the sheet in front of you if you're in class. If you're not in class, hopefully you received the handout. Mg cosine theta will end up equaling mg sine theta, and mu ends up being sine theta over cosine theta, which you know to be tangent theta. So we worked out previously once, and you'll find it in every physics textbook, coefficient of friction for an inclined plane is going to be the tangent of the angle of that inclined plane. All right, that's what it's always going to be. And so we worked that out, and in this problem, you could plug in Chugsville, and you're going to get, in this case, that theta is going to equal the inverse tangent of 0.8, or 39 degrees. So one needs to be able to obtain things like that for various causes. So you might need to know what the coefficient of friction is, and you know the angle. All right, but it's always going to be that way when the forces are balanced. It's always going to be, that's going to be the angle where it's possible to have motion at constant speed, 0 acceleration, all right, or just to hold it in this case. So there's that. Then I take us into the energy balance business. And so when I write the sum of E sub I don't mean internal, I mean initial. All right, the gazintas, E initial or initial energy has to equal the sum of the goes outas or final energies. So these are initial and final energies. So let me initial, final. So what do we have? Initially, we have the work done by gravity, which is a potential energy. All right, that's all that's happening initially while it's at rest there. And then, as you can see on your sheet, on the other side, there's all the work done by friction going down the ramp. And then there's, at the bottom of that ramp will be the kinetic energy. So when I say work done by friction, I'm going to remove this F off of kinetic energy because we know it's final. So we won't, you might want to kill that on the sheet where it says K sub F. It is the final kinetic energy, but since I'm using sub F for the friction of work, let's not confuse our subscripts, all right? We know it's final because it's on the right-hand side. Every energy balance, left-hand side's the ins, right-hand side's the outs, all right? Going left to right. And then MGH is what we get for work done by gravity, always. Work done by friction is always going to be friction times the length that it works over. And kinetic energy is always going to be 1/2 mv squared. Every go down the ramp energy balance starting from rest has that structure. And we've already done a pie chart that would have told us going into it, it's all potential. Coming out of it, it's kinetic and friction. All right. So we have this formula. And when you put all the stuff in, all right, so friction would be, it's mu times n, but the normal force was mg cosine theta. So we've done this a couple of times. So I have mu mg cosine theta times L plus 1/2 mv squared. Well, hopefully you can see, well, there's an m all the way through. And so you get this GH equals mu GL cosine theta plus 1/2 v squared. The mass ends up not being critical in it because it's common to everything and that doesn't change. If it doesn't change, toss it out. We don't need to bother with it. All right. So that gets us to the bottom of that first page in the handout. And like it says, this is just an example to kind of remind you of what we've done. You're not allowed to forget any of that. You must carry it all forward. And then it's a setup. So turning the page. You begin with GH equals mu GL cosine theta plus 1/2 v squared. And it tells you, use the zeroth law theorem such that your v squared term goes away. So zeroth law theorem says that ADS equals v bar dv, and hopefully you remember that that boils down to 2ADS equals the difference of the squared speeds. In fact, we developed the energy theorem from this from an algebraic standpoint before we did it by calculus. Well, the initial speed's 0, so that drops out. Delta S, that's the displacement associated with the acceleration that we're trying to compute, which is related to the speed of the object, which is a speed relative to the plane of the inclined plane. And so delta S is the length. So what I end up getting is that v squared equals 2AL. So there's that. But wait, there's more. Remember, we're dealing with an inclined plane. It's at some height and it has some length and it's at some angle. Ramps are right triangles. So in number 2, I believe, which factor in the equation that you just wrote, the yellow one on this video, is in the same direction as the acceleration of the cabinet? Well, there's 2 factors that are in the same direction. Well, actually, I guess 3. So what's one factor that's along the same direction as the motion of the cabinet? Not all at once. Maybe the speed, maybe the length of the track, and the acceleration. They're all collinear. All right. So what we're trying to do here is we want to, in number 3, it says convert all length terms to the variable L, which represents the length of the truck bed, the ramp in this case. And that's going to be important because there's work being done by friction in that direction. So guess what? The sine of theta gives me a relationship between the height of the ramp, which is critical to its motion. It's the reason that it's moving. Gravity is associated with that. And the length. So that means that h equals L sine theta. So what we can do is, instead of GH, we would have, let's see, GL sine theta would equal mu GL cosine theta plus 1/2 times 2AL. Well, the 1/2 and the 2 are going to cancel out. I have a common factor of length. That's going to cancel out. And so I have a g sine theta minus a mu g cosine theta equals acceleration. And hopefully, if you remember or you have the handout handy, you might recall that we already worked out that the acceleration of an object fighting friction on its way down an inclined plane is always the fraction of g that you see right there on screen, sine theta minus mu cosine theta. That is a difference of fractions, which means you have a fraction of gravitational acceleration, which we absolutely expect the acceleration down an inclined plane to be a fraction of gravity related to the angle of inclination. The bigger the angle, the smaller the fraction. Now we could predict that. We could just say, well, on an inclined plane, A is going to be some fraction of gravity that will get smaller as the angle gets bigger. But we probably wouldn't guess that it would be a difference of fractions. That would take a different kind of analysis like the one that we did. So now you have the same equation by means of energy that we developed by means of force analysis in a prior edition of the course.